Thank you. Yesterday we discussed about the deviance of generalized linear models. It is defined by twice of difference of log likelihood under saturated model and log likelihood under model consideration. Lower the deviance, better the model. It is also useful for comparison of two models. A model having the lowest variance, it is better. So to identify whether the added variable is important or not, we use the concept of difference of deviance, and it has been compared with critical value, and that critical value with degree of freedom, difference in the degrees of freedoms of deviance of model 1 and model 2. We know that deviance is asymptotically chi-square distribution. So by using the additivity property of chi-square distribution, we can say that the difference of the deviance is also having a chi-square distribution, and it has the degree of freedom difference of degree of freedoms of deviance of the model 1 and model 2 respectively. The difference of deviance is compared with the twice of difference of degrees of freedom, and if the value is higher than the twice of difference of degrees freedoms of deviance, we can say the second model having a preference over the first model. It means added variable is important for the model development. But make sure that deviance is useful for a comparison of the two models if models are nested in nature. Then we obtain the various form of deviance of members of exponential family of distribution like normal, binomial, Poisson, gamma, negative binomial, etc. We have also seen in the second lecture of deviance an alternative way of obtaining the form of the deviance based on PDF of exponential family of distribution. And that form is a function of a theta and b theta. If we know the form of natural parameter and b theta of a specific distribution, we can obtain the form of the deviance. And we have derived the form of deviance based on the twice of ls minus lm as well as based on the exponential family of distribution. Now in this lecture we are going to discuss about the residuals of a generalized linear models. So in second semester in the course of linear models and regression analysis, we have seen the various form of residuals, namely ordinary residuals, and ordinary residuals is given by yi minus yi cap. That means observed minus predicted value. Then second residuals we have obtained, that is the standardized residual. We call them as a Zi, that is Ei upon sigma, where sigma is nothing but the standard deviation of error, and we know that the estimate of the sigma square is MSC. So here we substitute it as a square root of MSE. Okay, but we have also know that the variance of EI is equal to sigma square epsilon 1 minus HII. So the estimate of sigma is not the standard deviation of EI is not the sigma epsilon, it is this. So we develop the third residuals, we call them as a studentized residuals Ri, and that is nothing but Ei upon square root of variance of EI, and that is nothing but Ei upon square root of sigma epsilon square 1 minus HII, and that is nothing but EI upon, if you substitute the estimate of the sigma epsilon square is MSE, so it is a MSE 1 minus HII. Okay, so this is the various form we have obtained. Okay, so this is the studentized residuals. Then we have obtained the press residuals. We call them as a deleted residuals. So it is given by E of bracket I, and that is EI upon 1 minus HII. And then we obtain the R student residuals. Sorry, that is the TI. No? TI is equal to EI upon variance of E of I square root. And what is that? It is nothing but the EI equal to, if you are substituting this and if you are getting this, so you can have the form of the studentized residuals. And then because the ith point is outlier, so here we cannot use the estimate of the sigma square as a MSC because we are deleting the ith residual. So instead of this we can use the SI square, and then we get the, that is EI. EI is, you can substitute 1 upon 1 minus HII, and here it is a square root of sigma square estimate is a SI square, and this is 1 minus HII. So it is a EI upon SI square 1 minus HII. Okay, so this is a kind of a residuals we are getting, and these all residuals are useful to take the decision about the whether the outlier is present or not. So any form of the residuals, let us say here it is a di, it is not zi, it is a di. So if the di is exceed 3, if ri exceeds 3, if t of I exceed 3, or e of I exceed 3, we say that ith point is an outlier. Okay, and then we also obtain the Cook distance. We call them as a di, and we say that if di is exceed 1, we say that ith point is influential point. Okay. So this is all we studied in the second semester of a linear models and regression analysis to detect if there any outlier present in your data or not. And then we have also make the various residual plots of the above residuals. Above residuals is known as the scaling of residuals because we apply the various scale over there. And then we make the plot, that is the normal probability plot. Then we make the plot of residual versus predicted value. We make the plot of DI, that is Cook distance versus leverage point HII, and based on that we take the decision whether the residuals follow the normal distribution or not, or is there any heteroscedasticity or homoscedasticity present in the data or not, or you can say that is there an influential point present in the data or not. So this is what we have seen in second semester, and these all residuals are stable residuals and having the normal distribution. But when we talk about the generalized distribution, these residuals are no more useful. And that is how one has to go for the residuals for a generalized linear models. So in generalized linear models, we will have a two residuals, three residuals we can use in generalized linear models. That is, first is Pearson residual, second one is Anscombe residual, and third one is a Deviance residuals. Okay, so there are three different form of residuals we will see in the generalized linear models, namely Pearson residuals, Anscombe residuals, and Deviance residuals. So we know that what is the residuals. Is it visible to everyone, or should I exceed?
Yes, sir.
Yes, sir.
Okay. So there are three residuals, as I say that. So what is the ordinary residuals? The ordinary residuals is given by, let us say, observed value is equal to predicted plus difference of this. So actually yi minus e cap is said to be a residual. So it is said to be y is a data value, this is the fitted value, and plus residual. So data is nothing but fitted value plus residuals. So residuals can be used to explore the adequacy of fit of a model in respect of choice of variance function, link function, and in terms of a linear predictors. So whether the model is adequately fit or not, that can be identified based on the study of a residuals. Residuals may also indicate the presence of anomalous values requiring for the further investigation. For example, is there any outlier in the data or not? So is there any anomalies present in the data or not? So that can be also studied based on a residuals. For generalized linear models, we require an extent definition of residuals applicable to all distribution that may replace the normal. Earlier, whatever residuals we have seen, that residuals is mainly useful for normal distribution. But we need a residuals which can be applicable for all members of exponential family of distribution, which has the properties of like it has the normal and having a stabilized variance. It is convenient if these residuals can be used for the same purpose as the standard residuals. So if we have some residuals and if you find out some kind of a residuals which has the property like the standard normal residuals, then you can use all the adequacy fit process through that residual analysis. So we will see there are three different kind of residuals, namely Pearson residuals, Uncombe residuals, and the Deviance residuals. So what is Pearson residuals? So whatever we taken the standardized residuals in the second semester, it is nothing but the Pearson residuals in this case. But here instead of the sigma, we are substituting the variance of mu. That is the variance function. The Pearson residuals is defined as the Rp is equal to y minus mu. Y is the observed value, mu is the expected value, and it is square root of variance of mu, where variance of mu is a variance function of mu. Probably you remember that we have obtained the variance of exponential family of distribution, where variance of y is equal to variance of mu into a phi. So where variance of mu is a variance function of mu, it is a completely a function of mu. So you can say that it is just the row residual scaled by the estimated standard deviation of y. The name is taken from the fact that for the Poisson distribution, the Pearson residual is just the sine square root of the component of Pearson chi-square goodness of fit test. So if you just take off this residual, then it has the standardized residuals, and we know that if it is a standardized, it has the square is a chi-square distribution. So if we consider the, let us say, Poisson distribution, then the Pearson residual square is follows the chi-square distribution function, and that is how we can have this relation summation Rp square is equal to chi-square. Here it is x square having a chi-square distribution. So it is a goodness of fit test as well, you can say that. But what is the problem with the Pearson residuals? It does not give the guarantee of the normality, and it does not give the guarantee of the stabilized variance, and that is how one has to go for the new residuals, which is the called the Anscombe residuals. So what is the form of the Pearson residuals? It is a first residuals is Rp is equal to y, that is the observed value, mu is nothing but the expected value of y, divided by the variance of mu, and variance of mu is said to be a variance function. Okay, but there is a problem with the Pearson residual is that it does not give guarantee of normality and stabilized variance. However, whatever residuals we have seen, like ordinary residuals from ordinary to the R student residuals, all residuals having a normality assumption, and they are the stabilized variance. But here the Pearson residual does not give, and that is how we will not going for the Pearson residuals. So that is how we have to jump into the, or we have to go to the Anscombe residuals. A disadvantage of the Pearson residual is that the distribution for a non-normal distribution of Pearson residuals for a non-normal distribution is often markedly skewed, and it may fail to have a property similar to those of normal theory residuals. So if your basic distribution is normal, then Pearson residuals give guarantee that it has the normal. But suppose basic distribution is non-normal, and if you find out the Pearson residuals distribution, so it is not normal, it is also a skewed distribution, and therefore it violates the property of the normal theory of residuals. So when I am saying that the basic distribution means it is a distribution of a y. If the distribution of y is a binomial, then Rp does not have the normality, or the RP does not follow the normal distribution. Okay. So Anscombe proposed defining the residuals using a function ay in place of y. So Anscombe said that okay, we will have the solution. Let us, instead of the y, you can use the function of y while defining the residuals, where a is chosen to make the distribution of ay as a normal as possible. So what it said that because distribution of y is not normal, of course its residuals also not normal. So therefore, can we make some transformation on a y, let us say ay, such that ay having a distribution normal as much as possible. So Wedderburn showed in 1978 for the likelihood function occurring in generalized linear models, the form of A is given by this. Okay, so he said that let us say what should be the transformation of y. So let us say function A is given by integration of d mu by v raised to 1 by 3. What is the v? V is the variance function. And what is the variance function for a Poisson distribution? So what is the form of variance function of a mu? Sorry, variance function in the Poisson distribution. So we know that the variance of y is equal to mu into 1. So fi is considered as a 1. So variance of mu is equal to mu. That is, variance function is mu. And just substitute over here. So it is a integration of d mu by mu raised to 1 by 3. And you take the integration, you will get the 3 by 2 mu raised to 2 by 3. So let us show into this page. You can have more idea. So what is the Anscombe residuals? They are saying that you have to have some form of y. Let us say a dot in Anscombe residual is integration of d mu by v raised to 1 by 3. And this is the function of mu. Okay. So for Poisson distribution, what is the variance of y? Variance of y is equal to variance of mu into a phi. But variance of mu was mu and a phi is this, so it is a mu. So what is the variance of mu? It is a mu. So just substitute over here, a of mu is equal to integration d mu, v is equal to mu, so it is a mu raised to 1 by 3. And when we integrate it, what will happen? It is a minus 1 by 3 plus 1 by 3 divided by 1 by 3 plus 1. Sorry, minus 1 by 3. So it is a mu raised to, what is that? It is a 2 by 3 divided by 2 by 3. So we can say that it is a 3 by 2 into mu raised to 2 by 3. Okay? Is that clear? Now, hello? Is that clear?
Yes, sir.
Good. So now what is the form of, this is the A of mu. So now we wish to find out the form of the Anscombe residual. This is the transformation we had applied. So wherever mu is there, if we are writing ay, then mu replaced by the y. So let us come back to this part. So that we base our residuals as y raised to 2 by 3 minus mu raised to 2 by 3. Let us how it come. Now the transformation that normalized the probability function does not as the stabilized variance. So this transformation suggests that the data having a normal distribution. So if you have data having a Poisson, and if you take the third transformation 2 by 3, it gives the normal. You can try it your level. You can use the R language, take the Poisson data, take the 2 by 3 transformation of the response variable, and when you make the normal probability plot and perform the Shapiro-Wilks normality, it is suggesting that it has the normal distribution. But here the problem is that it has the normal distribution, but it does not stabilize the variance, because we say that the variance should be homogeneous, variance should be constant. That is how we are assessing based on the residual versus predicted plot. So that we must scale by dividing the square root of the variance of ay. So we have to divide this quantity, that is the by the square root of variance of ay. And what is the variance of ay for the first order transformation? First order approximation value of variance of ay, it is the a dash mu into variance of mu. So it is saying that variance of ay, a mu, is approximately. Why approximately? Because I am talking about the first order transformation. What is that? It is a dash mu into square root of variance of mu. Is that okay? Sorry, it is the square root of variance. So what is the variance? The variance of a mu is approximately a dash mu square into variance of mu. Okay. So now our basic idea is that I wish to find out the Anscombe residuals. I will call them as a RA. So of course, we require the data point. So here instead of the original data, we take the transform. So it is a of y minus what is the predicted or estimated value or fitted value or expected value. It is a mu, and we divide by the square root of variance of ay. So what is that? It is a, this is the variance of ay. Okay, and this is nothing but, what is that? It is a dash mu 5. So what is that? It is a dash mu. You can, because we are writing in the square root, so we take its square into variance of mu. Okay. Now, what is the form of ay? So it is a 3 by 2 y raised to 3 by 2. What about this a mu? It is a 3 by 2 mu raised to 3 by 2. Okay. What is a dash y? So that we have to obtain. What is the form of a dash y? We have to obtain that. So let us say a dash mu is equal to d by d mu of a mu. And what is a mu in our case? Anybody remember? We have obtained it is a 3 by 2 of mu raised to
Yes, 2 by 3.
3. So just take 3 by 2 outside. What is the differentiation of mu raised to 2 by 3?
So
It
2
is
by
a,
3,
very good, it is a 2
2
by
by
3
mu
into
raised to
mu raised to 2 by 3 minus
minus 1 by 3.
minus 1. Okay. So
Minus 1 by 3.
this will be cancelled out. So it is a mu raised to
Minus 1 by
minus
3.
1
1 by
minus 1 by 3.
3. Okay. So what is the form of RA? RA is nothing but a mu, that is a of y 3 by 2, y raised to 3 by 2, and here it is a mu is 3 by 2, mu raised to, sorry, again
3.
mistake. It is a 2 by 3.
2 by 3.
Okay, it is a 2 by 3,
Hmm.
and here it is also a 2 by 3,
Hmm.
then square root. What is a dash mu? A dash mu we have obtained, but it is a square, so it is a mu raised to minus 1 by 3 square. And what is the variance of mu?
Mu.
Variance of mu is mu.
Mu.
So it is a mu. So it is a 3 by 2 y raised to 2 by 3 minus mu raised to 2 by 3 divide by
Minus 2, mu raised to minus 2 by 3.
mu raised to 2 by 3 plus 1. Can we? Can we write?
Minus 2 by 3.
Minus 2 by 3, na sir?
Sorry, minus 2 by 3.
Minus 2 by 3.
Okay. So what we'll write? It is a 3 by 2 y raised to 2 minus, sorry, it is a 2 by 3. Here it is 2 by 3. And this is the square root of, what is that? Mu raised to 1
1
by
by
3.
3.
1 by 3.
And when you take the square root, what will you get?
1 by 6.
1 by 6. Very good. Shabash. It is a 2 by 3 divided by mu
Mu
raised
raised to
to
1 by 6.
1 by
Hmm.
6. So this is nothing but the form of a Anscombe residuals for the Poisson distribution. So you have to find out the form of the Anscombe residuals for the various distribution. The general form of the Anscombe residual will be this. Okay, this is the form. You have to find out the form of AY. How will you find out the form of AY? Based on the form of A mu. And what is the form of A mu? It is nothing but the A.
Hello, sir. Can't listen you.
Hello. It is problem to everyone.
No, sir.
No, sir.
So I think you have to check your mic. You had some problem. Okay. So you have to have a mu is equal to integration of d mu v raised to 1 by 3 mu. So just you have to have an idea about the variance function of a specific distribution. Just substitute over here. You can calculate the a of mu, and if you know the a of mu, you can write down the a of y. Now what is the variance of a of y? So it is a dash mu whole square, variance of mu. So a dash mu is nothing but the derivative of a mu with respect to mu. So you have to calculate this, and then you substitute over here, you will get the form of the Anscombe residuals. So in short, to find out the Anscombe residuals, we should have the idea about the variance function of a mu. And how to find the variance function of mu? So we have already obtained the mean and variance of the exponential family of distribution, and we have also deduced the specific case of the mean and variance of the various distribution like normal to gamma, and where we obtain the variance function of mu. So b double dash theta, actually what is that variance of mu? Suppose if you don't know that, so you can also know this formula, variance of y is equal to b double dash theta a of phi. Okay, and what is the b double dash theta? We call them as a variance of mu. So if you know the function of the b theta, so take the derivative of b theta twice, and whatever you get the function of theta, convert them into the mu. It is called the variance function. And then use that variance function into Anscombe residuals and obtain the Anscombe transformation, and also obtain the Anscombe residuals. Okay. So this is what we have obtained. Similarly, you how to find out the Anscombe residuals for the various distribution. If you find out the Anscombe residuals for the gamma distribution, you should have this form. Okay. So here, okay. Okay, let us obtain the Anscombe transformation for the gamma distribution. So for gamma, what is the mu for the gamma distribution? What is the variance of mu? Anybody has idea? Variance of mu is equal to b double dash theta, and b double dash theta, I think we obtain mu square. Am I right? Or no? Idea anyone?
U square.
Mu square, no? That is what I told. Okay, we have obtained the, because variance of y we obtain mu square by alpha. So this is the mean and variance. Okay, so we can say that it is a b double dash theta is equal to mu square. So variance of mu is equal to mu square. So what is the a of mu? Therefore, a of mu is equal to integration of d mu by v raised to 1 by 3 mu, and that is nothing but integration over d mu divided by v is equal to mu square. So it is a mu raised to 2 by 3. And what is that? It is a mu raised to minus 2 by 3 plus 1 divided by minus 2 by 3 plus 1. And what is that? It is a mu raised to 1 by 3 divided by 1 by 3. So can we write it is a 3 into mu raised to 1 by 3? Yes. So what is the a of, sorry, variance of a of mu or a of y is nothing but the a dash mu whole square into variance of mu. But what is the a dash mu? A dash mu is equal to d by d mu of a mu. And what is that? It is a 3 times mu raised to 1 by 3 minus 1 divided by 1 by 3 minus 1. Is it? Or I made a mistake?
Second, integration taken out.
तो डिनोमिनेटर में नहीं लेगा.
Into.
लेगा वो इंटीग्रेशन में आएगा. सही बात है आपकी. ये आएगा into में.
Yes sir.
Okay, so
1 by 3 into right.
So this 3 will be cancelled out, and
Yes,
it is
sir.
a mu
Mu
raised
raised to
to
minus 2 by 3. Minus 2 by 3.
2 by 3. Okay, so now we will substitute over here. It is a mu raised to minus 2 by 3. Is it? Okay, let us note. And variance of mu is mu raised to square.
Yes,
So it is a mu raised to minus 4 by 3 plus 2.
Plus
So what will we get? It is a mu raised to
2 by 3.
2 by 3.
by 3.
Okay, so therefore Ra is equal to, sorry, Ra equal to a of y minus a of mu divided by
Under root of
a dash
A dash
mu
into variance.
square
variance of
variance of
mu.
mu. निश्चित आपका वो फैन का आवाज ज्यादा आ रहा है. Okay, so what is the a of y? A of y is, we have obtained, it is a 3 y raised to 1
Y
by
raised
3
to 1 by 3
This is the y raised to, sorry, mu raised to
mu raised to
1 by
1 by
3
3
because 3 is common, and this is nothing but the
root
square
over
root of mu raised to 2 by 3.
2 by
So
3
that is how you will get
minus
the
2
form of
by 3
basically 3 raised to y raised to 1 by 3 minus mu raised to 1 by 3 upon mu raised to 1 by 3. So this is the Anscombe residual for the gamma distribution. Okay, so it's very easy to obtain. You can obtain the form of the various Anscombe residuals. Okay, so in short, why we have to go for the Anscombe residuals? Because it gives the it gives the basic properties of the residuals like normality and the stabilized variance. So that is how we have to go for the Anscombe residual. And the third residuals, we know them as a Deviance residuals. What is Deviance residuals? So we have already obtained the form of the Deviance. What is the form of Deviance we have obtained? Deviance we obtain is a twice of Ls minus Ls. So we have the form of the deviance for the various distribution. We know that because we have already obtained it. So deviance residual is denoted by di, and di is nothing but the SGN function y minus mu square root of di. Square root of, sorry, square root of, this is the di is the notation rd is used. Okay, notation is rd. So rd, and I will tell that rdi, and where di is nothing but the contribution of the ith observation in the di, and when sgi is sgn y mu is, it is a sine function. It is a sine function. So sine function takes value 1 if y is greater than mu. It takes value 0 if y equal to 0. It takes value minus 1 if y is equal to mu, and y is less than mu. Okay, so SGN is known as a sine function. Depend on the relation between y and mu, it takes value either 1, 0 and minus 1. And di is nothing but it is a contribution of of ith observation in deviance. Okay, in deviance. So we know the form of deviance. Just write the di as a form of the deviance over there for the ith observation. So we will not use the summation sign. Okay, and then we can calculate the deviance residual. So this is what it is saying, that rd is nothing but the sine function of y minus mu square root of ti, and we know that this quantity is increased with yi minus mu I. Okay, so if yi is greater than mu I, the deviance residuals will take positive value. If yi is less than mu I, it takes the negative value. And if you take the square of this, what will you get? So when you take the square of rd square is nothing but the sine of y minus mu square root of di whole square. But we know that sine, if you take the square, so minus 1 square is always positive. So it is nothing but the square root of di whole square, and it is a di. Okay, and if you make the summation of all such residual square, So it is nothing but the summation di, and summation dy is nothing but the deviance. If you remember the formula of the deviance, we have also obtained that all the deviance having the double summation and then some quantity. So that quantity is known as a di. So what is the, if you remember the form of the deviance, what is the form of deviance for a Poisson distribution? What is that for Poisson distribution? It is a
Mu.
d is equal to, or d or s, you have used the notation s, so you can say s. S is equal to summation yi into log yi upon mu I minus what you have written, yi minus mu I. Mu I की जगह पे हमारा क्या था, fitted value था, तो this is the mu I cap. Okay, this is the form of the deviance for a Poisson distribution. Am I right? Yes or no?
Yes, sir.
Yes, sir.
Of course, the twice is multiplied with that. So this 2 is inside. So this is what the minus they have just taken. So it is minus yi plus mu I. So this is what. And because you are finding the Deviance residuals for a Poisson distribution, so this is the contribution of the ith observation in the Deviance. And you just take the square root. So this is di. So di is nothing but in our setup, di equal to twice of yi into log yi upon mu I cap minus yi minus mu I cap. So this is a contribution of the ith observation in the deviance. Okay, and then as I said that if you take the okay, so here it is a di, so you can see that here if I have taken the square, it is the sum of di. So how many such observations? There are an observation. So you take the sum of this, it is giving the deviance. So to obtain the deviance residuals is a very simple. We should know the form of the deviant. Just take the square root and apply the sign function. If y observed value is exceed the predicted value, of course, then you can have the positive sign of the standardized, deviance residuals. If yi is less than mu I, then you have a negative sign. Equal to 0, then the deviance residual is 0. So you can either use the Anscombe residuals, or you can use the Deviance residuals. But people are more comfortable with the Deviance residuals because Deviance residuals is also satisfy the basic assumption of the normal residuals, that it has the normal distribution and the stabilized variance. So you can find out the various form of the residuals or Deviance residuals for the various distributions. Any questions, anyone up to this?
No, sir.
So it's a very simple to obtain the form of the Deviance residuals. Okay, let me open this book where. Yes. So, can you see this?
Yes, sir.
Okay. So suppose if
Yes, sir.
I am interested to find out the form of the Deviance residuals for a binomial distribution, then what should be the form? So what is the form of deviance? So we know that here in binomial distribution, it is a deviance having a twice of summation, but we will just contributing the ith observation. So it is a twice of yi into ln y upon
And
mu.
then y
So,
final, yeah.
so this is here they have written it is a n into pi I cap, because if it is of a binomial distribution, then ni minus yi ln ni minus yi and ni minus ni pi I cap. So instead of pi mu I cap, they have taken here the pi I cap. Suppose your yi takes value 0. If you talk about the group data, if yi takes value 0, so then you have to substitute yi equal to 0 here. So this part goes, because 0 multiply this, and this part is also going to what you will have ni into ln 1 upon 1 minus pi I. So 1 upon 1 minus pi is the sign is the minus, so that is the twice of n into L minus pi I. And because the yi is 0, so this become the minus sign. And when you take the yi equal to n, then what happen? This become the positive sign. So this entire quantity gone, because ni equal to yi. So this part vanished. So what you will get? Ni into ln, ni cancel, the 1 upon pi I. So it is a minus of ni into ln pi I. So it is a minus twice of that. So you can obtain the form of the deviance residuals when y equal to 0 and y equal to group data. If it is of a row data, then you can have another form. Okay. So this is the form they have given anyhow. So then once you have this, all the things, you can find out the standardized residual, deviance residuals and other things, but that we will see in the later part. Yes, any questions? Anyone? So we have seen the various form of residuals. In second semester, we have seen the residuals like ordinal residuals, standardized residuals, studentized residuals, trace residuals, and R residuals, R studentized residuals. But these all residuals satisfy the properties of a normal residuals, like it has the normal distribution and
Calculator.
hello. So these all residuals have the property of normal distribution, like it has the normal distribution and the stabilized variance. But that is not true for the generalized linear models. So that is how we are looking for a residuals which satisfy the properties of the normal residuals, like they have the normal distribution and stabilized variance. And that is how for a generalized linear models, we have developed three form of residuals. One is Pearson residual, second one is Anscombe residuals, and third one is Deviance residual. So Pearson residuals is nothing but simply a standardized residuals. It is given by the y minus mu divided by the square root of variance of mu, where variance of mu is a variance function. But the Pearson residual has the problem that it does not give the normality of the residuals and stabilize variance when the distribution of y is non-normal. And therefore, Anscombe Vedamban has given the form of Anscombe residuals, where Anscombe is a kind of a transformation on a y. It will transform your original response into the normal response, so that whatever residuals you are getting, it should have a normality and stabilized variance. So Anscombe transformation is nothing but integration of d mu divided by v raised to 1 by 3 mu, where v is nothing but the variance function. So you have to obtain the a mu. Further, we know that what is the variance of ay. So it is nothing but the a dash mu whole square into variance of mu. So Anscombe residuals having a normal distribution, but they do not have a stabilized variance. So that is how that residuals is divided by the standard deviation of variance of ay, and therefore the Anscombe residuals, which is given by Ra equal to ay minus a mu divided by square root of variance square root of a dash mu whole square into variance of mu, which has the normal distribution as well as the stabilized variance. And we have obtained the form of the Anscombe residuals for the gamma distribution as well as the Poisson distribution. Now we can go for the third residuals, that is of a residuals based on the deviance. So we know that the deviance is a measure of discrepancy. It is a measure of goodness of fit of the generalized linear models. So if we know the form of the deviance, we can easily find out the deviance residuals. And further, this residuals has also the both the properties of a normal distribution, like it has the normality as well as the stabilized variance. So how to obtain this deviance residual? So deviance residuals is denoted by the RD I is equal to sine of yi minus mu I into square root of di, where sine of yi minus 1 function, it takes value 1 when y is greater than mu, it takes value 0 when y equal to mu, and it takes value minus 1 when y is less than mu. And so based on that, you can find out the form of the deviance residuals. It is very easy to obtain because we know the form of the deviance, and form of the deviance is, let us say, capital D. So that is nothing but the summation di. And what is summation di? And what is the di? So di is nothing but the contribution of the ith variable, ith observation in the form of the deviance function. So r di is nothing but the sine function of y in sine function of y minus mu into the square root of di. So that is how, if you take the square of these residuals and the sum of the square of such residuals, it is giving the sum deviance. That is nothing but the form of the deviance. Okay, so I think this is all about the story of the uh, residuals in the generalized linear models. In next lecture, we will see about the fitting of parameters, or you can say that the estimation procedure for a generalized linear models. Any questions to anyone in the lecture of the residuals?
No, sir.
No, sir.
Okay, so in this week we should continue with the one more practical, or we can go the practical or the next time. Otherwise, I am thinking to introduce the practical on